Okay, I started to say, I actually said something misleading. I erased it, so it didn't exist. Hopefully I won't post the video. Okay, L is I omega. I is the sum of your MR squareds, or the integral of your MR squared. Okay? And you multiply that by omega. Which is sum of your MR squared times dr dt. And it's not dr dt, it's d theta dt. So now we have angle theta. As this thing moves around the orbit, theta changes, right? Okay? Well, if L remains constant, when your sum of your MR squareds is changing, and why is it changing? Because at every point except this one and this one, your distance from the center is changing, right? Your distance from the planet is changing. At apogee and perigee, your distance isn't changing, right? Okay? So if L remains constant, then except at perigee and apogee, R and hence MR squared is changing. So that d theta dt changes accordingly. Okay? Because L stays constant. If this gets smaller, this gets bigger. If this gets bigger, this gets smaller. Okay? Well, you can also say that L equals mvr. Okay? Except it's actually m times v perpendicular times r, again for reasons perpendicular to the r vector. Okay? In rotation, the perpendicular always will, unless otherwise specified, refer to perpendicular to the r vector at a point.
Not the orbit?
Huh?
Instead of the orbit, it will be the r vector?
Yeah. So, for example, here, what causes theta to change? Does theta change because of motion component in this direction? I mean, here, your velocity is like this, right? It has a component in this direction, it has a component in this direction. Which component causes theta to change?
The one that's not toward the center?
Yeah, one toward the center doesn't change the angle, right? So here you have V, here you have
Damn right.
V V perpendicular, and of course you'll have your V parallel, and I'm not going to clutter up the picture with, okay? So you have L equals M V perpendicular times R, okay? Well, all this comes down to the following, and this is what we need in order to do the thing I'm going to want you to be able to do and kind of ask you to do on homework last night. I only got one homework and you came close, okay? Almost got it. If I know the mass of the planet, the speed and distance at perigee, then using this, I can find the speed and distance at apogee. Okay?
But the speed is 80% of what it would have to be in a circular orbit.
At perigee and apogee, V equals V perpendicular. Because when you're up here, you're moving in this direction, which is perpendicular to your R vector. Down here, your R vector's here, your direction of motion is here, right? That's all there is to it. Okay? So this is your velocity at perigee, this is your velocity at apogee, right? In there. Since L is constant, this is the expression at perigee and apogee, and they're equal. Okay? Now the other thing in the last problem that I assigned, so I said, okay, I gave you velocity and distance here, gave you the mass of the planet. I don't remember if it was Earth or something else, but you had the mass of the planet. Okay? And then I think I said, okay, you're in circular orbit here. And of course you set centripetal acceleration equal to gravitational force, centripetal force equal to gravitational force, figure out the velocity. Okay? Whatever. Let's say, okay, you lose 1,000 meters per second in your velocity. What happens? Well, you're not moving fast enough for your centripetal force and gravitational force to be equal. So now the gravitational force is greater than your centripetal force and you start falling toward the planet. Of course, you still move in this direction, so you don't necessarily hit the planet, although I think there was at least one terrible collision with something in some of the work that I saw. But that's just, you know, that's in the arithmetic. Okay, so we have the situation where if we let this distance here be unknown, we have two equations for that distance. Okay? We know what our potential energy change would be in terms of this distance. So we know what our kinetic energy change would be, so we know what our velocity change would be. But it has to satisfy this as well. So there are two restrictions on your velocity at apogee, perigee in this case. At perigee. Now, I don't know if I was calling these right. This is apogee, that's far away. This is perigee, that's close. Okay?